Let's see. All right. PowerPoint. You guys have any questions? Anything like there's one group has a question on the homework. I'm gonna ask something, but and then anything else like the new homework? Everyone, no one looked at it. Probably. Anyway, all right. So
Can
you have questions?
explain the bi-bubble, like why that matters in the first question?
All right. To so chart, it's not to Huckle. Huckle's when you have like an interface for like a charged species and it sets up layers. Like there's a first layer of counter ions and the opposite, and it goes off into space. And there's like a length in that. So Debye Huckle's separate from Debye screening length. They're kind of they're related, but they're separate. So Debye screening is just that. So you add salt for this coacervate, and the salt's acting as like a blocking. So it's as if you're putting more. Say you have a person yelling for their little kid over here, and then all of a sudden it's in a big train station filled with people, and you can't hear the kid anymore because of the other people. It's like the opposite charges are coming in blocking that. So that means that in this case the two polymers are going to stick together plus minus, right? And that's going to make slime basically. So, or in this case, an adhesive. So if you put in enough counter ions into it, they can't see each other, so it can't make slime. So it's just a liquid. So then you can inject that. And then when it gets into the body, it's at a much lower salt. So not in the, so the train station empties out. They get on the trains, and then you can see the little kid over there. Then all of a sudden,
that's annoying.
Right. So that's kind of the idea that by screen like it goes with 1 over the concentration, the square root of the concentration. So that's also called soap. Salt into it, it won't be soap anymore. It'll just be like oil. It'll be like a mess. So you can't wash off if you have water or something. It's like the hardens. You ever, and what is it, hard water or soft water when you get slime all of these? So anyone, hard water. Okay, so like if you ever go to someone's house or your house and it's like hard water, you go to take a shower, you never really get slime soap oil thing on you. That's salted out, whatever. So that's Debye screening on your skin, I guess. But and also you can add salt. There's some of the cases where you add salt and then the thing falls apart, right? Where you can take like a jet, if you dump salt into that, it'll just turn into just water, like salt water, because there's only like 1% or 0.1% of the polymer in it. So it's like nothing. So the whole thing that's holding it together is just this 0.1% of stuff. So there's a lot of, you'll hear like salting out. People talk about salting out. That's got to do with that. So, and in this case, they're making it injectable by dumping a bunch of salt. And then when it gets into your blood, you're at a lower salt, and then it can stick and make an adhesive, and like stop you from internal bleeding. That's the idea. So, I mean, you can, there's a link to the Debye screen link here that talks about it, but actually it's not readable. Like if you go to that, this isn't readable really until you get, there's an equation for the Debye screen length, which is somewhere in here, like this thing. So Debye screen length, and this is sometimes called kappa to the -1. Like they'll do 1 over this is kappa, this kappa, not that kappa, it's Boltzmann, but there's a kappa that they Debye kappa, which would be NE squared divided by that thing. And then square root of, oh, here's kappa, right? So anyway, so that's kind of, there's another thing, this Jirum length, which I can't pronounce, but that's kind of the same thing, except it's got to do with this. It's like a unitless number, like a chemical engineering unitless number. It's like the balance between the charge, the Coulomb forces, and KT, the Boltzmann forces. So Boltzmann's going to make things diffuse, like jog around, and the charge is like sticking or pushing away. So you end up with a distance for which Boltzmann diffusion overcomes the charge thing. So that's about it. I mean, it's a good question. I mean, anyway, I talked a little bit about that, so hopefully you can put that together. All these are like pieces of stuff that, so you'll see a paper or someone will be talking about something or whatever at work, and then it'll come up like you pour salt in to do something to it. And usually that's gonna be the counter ions are going up and you're trying to reduce this coulombic interaction. I'm not sure where you run into it, but I definitely run into it, the hard water thing, right? So I guess there's a lot of ions in it and they block the soap from making micelles. So, all right. Never went through, oh, yeah, actually, I never went through this linear viscoelastic question, but basically, that's got to do with the, that's described in this, that's described, I put a bunch of links here. So this is, it's just, here, it just says linear rheology and it kind of talks about, so they show, this is from a viscometer company and, stress strain are proportional. That's what they mean by linear. So in other words, you can write an equation like stress equals viscosity times strain. It isn't some weird thing. Well, they aren't proportional anymore. So it tails over. At high strain, you get weird things happen, melt failure or something like that. So it's just it means you're at a low. This is strain amplitude. So you're oscillating the strain, and then there's a magnitude of the amount you oscillate. So usually you're going to be, and this is in percent. Usually you're operating at like 0.1 to 1% for this kind of vibrational rheology measurement. So it's literally just a speaker. It sounds like a speaker. It's just like vibrating just the amount that a normal speaker, like the core of a speaker would vibrate. So it's basically the same thing, except it's going in a rotational instead of a linear way. So I mean that's the whole what is linear. So they'll always say we're doing linear viscosity. So it's kind of, they explain what it is in this thing. Just kind of tells you what it is. Anyway, I didn't mention that last time, but it's a lot of little things in this that, I mean, think of it as like pieces of a puzzle, and each one you pick up or like tools in a toolkit kind of. And then you need a screwdriver sometime, and it's going to be the device screen. I mean, and then so each one, even though it seems like, oh, there's a lot of little tidbits in this paper, but each one of them, it's teaching you something like a tool that you're going to use, and everyone's using the same toolkit, right? So everyone's kind of assumes you know about these tools. So so anyway, maybe the idea isn't that complicated. Maybe it's good to take a look at it and figure out what's going on. Anyway, so anything else? That's good.
Just sent another email this morning to another person who may have information on LinkedIn.
I didn't hear the last part here.
So we will see how that works. So
I think you're talking to someone else.
they live on the West Coast, so it might take some time.
We could just listen.
West Coast.
I can mute them.
That's the wrong person.
Oh, wrong person. Okay. Oh, no, I can mute him. This I can. Oh, everyone else is muted. All right, good, thanks.
Flashback to the one time during COVID era where my OChem one professor accidentally unmuted everyone and found people cheating.
Oh, that's pretty funny. Did they cheat?
No, it was, I think it was way.
That's pretty funny. I don't, yeah, it doesn't look like you can.
You can only ask unmute.
Maybe if you started,
It was in WebEx, I think.
if you start unmuted, maybe you can, like there's a generic mute everybody, I think. But actually, I must not have that on, but
I specifically turn my off.
yeah.
Yeah.
There you go.
What was that link again that we were just at, just so I can?
All right, it literally says linear viscosity. you should have seen this webpage before. It was like so many links. Like, it was just, and if you click onto old whatever, you'll see. But anyway, it's much easier now, you know. But so even though right here, linear rheology, yeah, but it'll be in a different, I mean, if you shrink the window, it'll be different. There's a lot in here, yeah.
But for like part B, I was just a little bit confused as to like maybe like more things I could read to like understand like where we would find the PEOs and like the PPOs like in like the article that we read, because I couldn't like draw like that line between the two, so I'm just confused.
Yeah, like the last week, there was a chemical engineering seminar and a guy was doing these fibrous protein clusters. And then he attaches like biomolecules to it. And then finally, he wants to make it so it'll go into the mucus under your tongue, which is also a coacervate. You know, but basically he sticks PEO on it. And he says like, all right, so some people are allergic to it. He mentioned that. But anyway, so it was the same kind of thing. So you have something complicated, and then you're just looking, this is like a touch point where you're gonna find something simple and something complicated, you know. So I guess it's this picture, but he shows it again later here. So here it looks pretty complicated. All right, it's a block copolymer. It's an acrylics. That's common for like something that's going to go into water, because this carboxyl is going to be a charged group to go in, and then it's got a sulfate group. So that's our surfactant. Like this part, if you cut that off and made the chain longer, that would be SDS, sodium dodecyl sulfate. It was a 12 carbon. They sticks that onto a, so it makes it polyanion. And then he wants to make it so put in a hydrophilic group, so the green thing, so he sticks this thing on. So it looks complicated, but this is just ethylene and oxygen. So that's polyethylene oxide or PEG, polyethylene glycol. So it's just stuck there. So this thing alone would be PEG. If you stuck a propylene on it, it would be a non-ionic surfactant. Or if you stick this onto any kind of aromatic group, like Triton X100. So you'll see this over and over. That's kind of the point. Somewhere, see, Triton X100 is a common thing in ink, right? So you have PEO right here. So PEO is the active group. That's the point. And then something that's oleophilic, like that would be the tail on a surfactant. Or here it's something you put into ink to get the ink to go in. I mean, you'll see that this thing all over the place. I'd say, I mean, it's weird because I worked with this once and then I started noticing the name and I realized like everything has this in it. Every kind of product has this stuff in it. You know, it's just like gets it to go into water if you have an oleophilic type thing. So it's a surfactant kind of. It's a non-ionic surfactant, it has no ions. So anyway, so that's the PEO thing. Anything else on this, sir? All right, so yeah.
I remember you doing something on the projector type thing where you took the delta G equals delta H minus
Yes.
delta S.
Yeah. All right, so yeah. Yeah, all right, so that's thermal, right? So that's just okay. So this guy's should be on. I think I put it on. Oh, dot cam's already on. Wait, is that right? Oh, did you guys? Okay, you didn't see what I clicked here then, I guess. Oh, wait, no. I must be hallucinating again here. Right. For this guy to go. All right, so anyway, all right, so yeah, so you just have like the Gibbs free energy is like the enthalpy minus T delta S. Have you seen that before? Okay, that's good. So you have like E to the minus delta E activation energy over KT for something like viscosity. Right. So it's a temperature dependence of viscosity. So if you take N over N naught, that's our like AT. That's our shift factor. That allows you to measure the viscosity at some temperature T versus the viscosity at some other temperature or some base temperature T naught. Right. So this would be your T naught in that case is 0K. So if you want to make this more meaningful, if something has a glass transition where it has no viscosity below the glass transition because it gets stuck, right? Then you add in another temperature, a Beaucage temperature, that's like bird in German. And it's just the guy's name, but there actually is an English name bird, right? When people name birds. So anyway, yeah, I'd like to know the origin of that word. It's kind of weird, but anyway, so and then the energy, this is energy, that's energy. So you just say that this energy. So say you have, normally the idea is like you have your liquid and this thing has to move. So these things have to move out of the way in order for that thing to go over here. And that's got an activation energy to it, EA. And that's the basis of flow. This thing like not. All right, that's pretty weird. Is that better? This better. Oh, EA is like the energy to move the other things out of the way. These are like molecules, atoms, whatever. So the viscosity means it involves that energy to move the things out of the way. But when those things move out of the way, say they get closer to some other things and that affects something else. So there could be an ordering change that happens. So that ordering that happens would be like a delta S. Originally, this EA is just an enthalpy, like it takes, because you're crowding together, there's a repulsive enthalpy, delta H. You could also have an ordering that happens when flow happens, particularly if you're flowing something like that and it goes to that. This has a conformational entropy of 0 because it's a straight line. It has no bendability to it. And this has a conformational entropy that's like something to do with NL squared. It's got to do with the molecular weight. So anyway, so anyway, so you could say that this energy has two components. In that case, this term up here would have two parameters. It would be like delta H minus T delta S over K times T minus TV. Right? So then you'd get that argument up here, like negative of that. So then that way you can get like 1 parameter, 2 parameter, 3 parameter. And in the WLF, which is the standard format for viscoelastic time temperature superposition. So you're gonna do a time measurement and frequency where you're oscillating the plate, right? Do the frequency measurement, and you're gonna do it at room temperature. And then you're gonna do it at 100 degrees C and at like minus 50 degrees C. And then you want those all, so those 3 curves would be like that curve for G prime, and then maybe it would be like here and then there, right? So, oh, sorry, yeah. So you want to get those to all overlap with each other, or it will be different parts of the same curve. So it'd be like that. Hard for me to draw it exactly, but it'd be those 3 parts, but they wouldn't be connected together. This shift factor, so this is say at room temperature, and then if you use the shift factor, it'll move this guy back to do frequency times AT instead of frequency, and it'll bring those all into this one curve. It brings them back together. So that's called, because you're transitioning time with temperature. So it's called time temperature superposition. So you can shift the things around. You just basically, normally just the Arrhenius function is fine, like a 1 parameter fit. Like if you plot the viscosity of anything versus 1 over T, you'll get a straight line basically. Almost anything, right? Until you get like really close to the glass transition, or there's some super kind of ordering happening and stuff, right? But if you're doing this at 0.1 strain, so such a small strain, there's not much ordering happening. So maybe this S thing isn't much of a factor. So generally, just the Arrhenius is fine for almost everything. And so that for polymers, it gets a little bit dicier because of glass transition. So you end up with this WLF is a standard format for doing that, right? So anyway, yeah, this is exponential, like N0, N equals that thing like that. So you can take the WLF, which is just going to have like C1, C2, C3. It's not in that form. And you just say, I think C3 is T minus TV. And then C2 is something else. So they're count, you can figure out if you set this thing equal to whatever the WLF form is, you can figure out what C1, C2, C3 are. So you can say they're the same thing. They both have 3 parameters. And in this case, you can say what the parameters are. WLF, they just seem to be just like something empirical, someone made up to make it fit a curve, which is what they were originally. But WLF, they just tried every form they could and they ended up with that form. I mean, they weren't thinking about it. So if you think about it, it's basically, then the Germans kind of came up with this Vogel temperature. And then this thing, I think I just put that in, but I think someone else has talked about that at some point. But anyway, you can just get these things back to something realistic, you know. Like you won't find exactly this form in any book, I don't think, but I think that's basically what it means. You might find it. There's a paper there. I'm not sure that if that paper has that. All right, there's a paper here back on the web page. No, that's not what I wanted. Looks like the right thing. I need to click that. So there's a paper called the homework. All right. Da, 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 da. Here, WLF versus Arrhenius. Actually, I haven't, yeah, so he's got the same kind of thing here, right? I mean, I think he kind of goes through the same thing. What I just said, more or less, you know. You can look at this if you want. I'm not sure he exactly goes through it that way. Like he doesn't say enthalpy and entropy in here. But I think he relates the Vogel temperature to that C3 term or something like that. This looks pretty familiar, you know, so anyway, that might help. So anyway, that's a good question. So that's a good, that delta G, delta H minus T delta S is a good thing to remember because it allows you to understand a lot of different things. Like what complex formulas like this WLF looks like a mess and you can kind of pick apart what it means. So it's handy to have that expression. That's one of the few thermo expressions that everyone will remember. Because it makes sense, like you can take apart the thing into energetic things and organizational things. So you can say the energy has to have those parts to it. Anyway, is that okay then? Any other stuff? Nope. All right. So, all right, I wanted to go through stuff. So all right, so Flory, like Flory's books in there. So he has initially the first part of the book, he says like defines these 2 terms like short range interactions and long range interactions. So he has this squiggly chain like that. So you'd think that long range interactions would be like something long, but it isn't. So all interactions are short range in terms of distance. In other words, all interactions are going to be like, if you break this chain into monomers, so maybe it's going to be up to like 5 monomers away. That's all interactions. Not everything beyond that is nothing. If you can't see it, it's too far away. You know, so even coulombic interactions, some strong interactions aren't going to affect anything more than a small distance away, right? So why did Flory say this business? Is because there's 2 things that can happen. Like if you have a squiggly thing like this, you can have like index 1, 2, 3, 4. So index 1 interacts with index 2, or like -1 or whatever, right? Or 0. So if you have, that's called a short range interaction, like a neighboring thing that happens. So say Flory was working with a lattice, so he was going to say like, oh, I'm here, and then I'm going to take a random walk. I'm going to pick any of the 6 directions in 3D. So I'm going to go that way, right? Then so I'm here. So if it's a random walk, I can go like that way, right? But you can't because the thing you just came from is there. Right, so you only have like 5 choices actually now after that, right? So that means that you don't have the that choice anymore. So that's what he calls a short range interaction. Right, so anything, if you go down the bond, so you have carbon-carbon bond is going to be like a tripod with a flagpole on it. Right, so if you and your chain's going to go like on a leg of it like that. Then you have these 2 things sticking out in 3D space, and then these things can spin around, right? So you can, if you have, say you have an R group like an acrylic group here, so that would be our polyacrylic acid. Then in the paper, then he's going to add the PEO to that, but so or whatever he sticks on that. Anyway, so if this thing, it means that if you go down this chain, this rotational energy changes depending on so you're going to have another carboxylic here, right? So those things, they don't want to be on the same side of the same kind of direction, right? In 3D space, they interfere with each other. So if you did a rotation about that bond, you'd find out there'd be a huge energy barrier for that when they're overlapping each other, and there'd be a minor one when it overlaps with a hydrogen. So this is a hydrogen here. So when that thing spins around, it overlaps with a hydrogen. It's a weak one. And there's another weak one. So there's like 3. It's like a 3 toggle switch with minima in it. It's got a global minima when the 2 carboxylates are opposite each other. There's a big dip over here. So you think of it like a toggle switch. It's got a really happy position and kind of marginally happy position. In some positions it really doesn't like. So it's going to be hard to turn the knob over that thing. Right. And then it's going to go zoom right into there. So there's energy here. There's also KT energy. So the stuff is actually spinning around all the time. So if it's cold, it's kind of stuck in the wells. If it's hot, then it's going to be like up here. So it's going to be the looseness of the switch knob that you have is going to depend on the temperature. The higher the temperature, at high temperature, it'll just spin around like crazy. No sticking. You're going to have like room temperature that has stickiness, and then the cold temperatures will just be stuck, right? In terms of the spinning around, that'll be a short range interaction. That's like the first thing that Flory kind of thought of was this rotational isomeric state model. RISM is what he called it, right? So basically, that's a short range interaction. Long range interaction is I'm going along and I've forgotten where I was. Like I'm just drunken walk, they call it sometimes. So you've forgotten where you were. Then all of a sudden, oh, I ran into the same chain, Well, I mean, that can't happen. So I have to go somewhere else. Well, because you go somewhere else, like the size of this chain was originally like the mean squared distance was NL squared, the number of steps times the length of the step squared. All of a sudden it becomes that R by L goes with N to the 3/5 instead of to the 1/2 here. This would be R by L goes with N to the 1/2. So that means that the chain size could kind of go up by a factor of 2 or something. If you have this kind of interaction, depends on what N is. If N is 1, they're the same. If N's a billion, then it's a pretty big change. So the bigger N, the bigger the difference. So you can think of that as some bigger kind of thing that happens. And because it's not something that you can put your finger on, like you can't draw a picture of this kind of rotational thing or this avoidance thing, then that becomes like a statistical picture of what's going on. Right. So that's called a long range interaction. So those 2 things are right. So if you take a polymer and put it into a solvent, like take polystyrene, put it into toluene or gasoline, you have napalm. And then napalm, if it's dilute, it's going to be this way. So your normal state for the polymer isn't this random walk Brownian motion thing. It's going to be this self-avoiding walk. That's really the native state. That's the native state. So everyone would think that, like, say you take a piece of plastic and the chains in it, well, you would think they're going to definitely hit into each other and they're going to have that expanded state. But Flory postulated that there was a kind of screening that happens, in analogy, I guess, to the Debye screen of charges. But this is a screening of the interaction energy between the chain components when they get into a melt. that they act as if they can pass through each other. So they act as if they can be a random walk at that point. So anyway, so that means you get, Flory proposed this, that random scaling would apply to a chain and a melt, which is most of the time, if you have plastics, that's the way it is. It's a melt, right? So it's only in solution that you would see this thing. All right, it turns out that was kind of a bold proposition, I guess, to make, because it didn't seem obvious. Still doesn't really seem that obvious that that would happen. In other words, the chains, just because there's other chains there doesn't mean that it would look like there's no other chain there because of the screening thing. In fact, the whole screening thing is a little bit hard to grasp unless you're in a train station trying to find a kid. Then you realize, yeah, it's true. There is a screening length, you know. So the same kind of thing here. Anyway, so I mean, if you tried to describe to someone that you couldn't find your kid, he was 8 feet away, you know, they would find it hard to believe, you know, but it can happen. So anyway, so screening happens, and Flory was proven right, and that was like one of his most glorious moments, I guess. That was like Flory's coup d'etat type thing. So anyway, so the traditional way in his book is to start with this thing. I think another thing is that he was kind of drawn, so he did a lot of work doing this random walk thing, and then to have someone come along and say, like, no, that isn't the way things are. There really is a self-avoiding walk, like this expanded coil, this long-range interaction. So all the stuff you did is worthless. So you spent like 10, 15 years working on that, and then it's like, you got to just throw that away. And so that's partly why maybe he was motivated to say that's the way it was in the melt. Then came up with an argument for why it was. So anyway, so the first part is to talk about the random walk thing, and that's basically is basically modeling the chain as if it's Brownian motion. Like I showed you pictures of diffusion path, and a chain is the same thing as a diffusion path. The advantage of that is there's a lot of equations already done from the, I guess Brown was in 1853 or something in England. Let's see, no, yeah. Anyway, they're all in the 1850s. So the stuff about Brownian motion had been around a long time. And then Einstein, I think it's like 1905 or something, came up with this thing about Brownian motion. So yeah.
So the main takeaway from like the short range versus long range is that like the short range has the rotational energy changes based off of like the bond structures, or is it more?
Yeah, it's anything. So it includes also that it can't take a back step. Anything that happens on a local scale. So say you have a polyelectrolyte and you have a bunch of positive charges on it. So it's a polycation. So the plus charges are going to repel each other, or a protein or DNA, right? So the charges on it repel each other. So that's a short range interaction. It's coulombic interaction. It forces a chain to turn into a rod, right? So anything that's local. Any local in terms of distance along the chain, like index 1, 2, 3, 4, 5, maybe, that's a short range interaction. And then what is kind of a no man's land. And basically, if you go to infinity, that's definitely long range interaction. So it's a matter of the one thing you can do a mathematical calculation of what it's going to impact. And the other one, it's a little bit more esoteric, like how it impacts it. So it's a little fluffier.
That's when the long range is when the chain interferes with each other.
Yeah, it's just a path when it gets far away and then it comes back and then they interact. So they're both short distance interactions.
Yeah.
And Flory called them range. I mean, he called it short range, long range. So you'll see like long range, short range, people commonly use those terms, but it doesn't, and you're led to believe it's a long distance, but it isn't. They're all short distance. It's just the index along the chain, and the impact of it's different. And the short range is going to impact the step length of the chain. So in the long range is going to affect the scaling of the chain, like how the size of the chain goes with the molecular weight. So they have two totally different effects on the thing. They both like if you increase the step length, the chain gets bigger. If you increase this interaction, the chain gets larger. But so they both make the thing larger. They just do it in two different ways. So in terms of like a chain size and solution.
but tries to like self-avoid for as long as possible until obviously infinity, and then it'll go back. Is that right?
No, it's like you're doing a drunken walk, right? So, see, so I don't know, you ever have, I don't know if you run or something, you have this like run keeper thing, it tracks where you go, or your watch does it. So you can, and then there's a program where you can spell out letters. Have you seen that? I don't know. Anyway, there's some program you can spell out like your name, you know, where you run. So you can run and then like run back and whatever, right? So anyway, that's the idea. Like, so that would be a long range interaction. Like if you go out here, say you want to make an infinity symbol. So you run it along, and then you finally get to here, and then that's a long range interaction if that was a molecule, right? So you hit each other here. Short range would be like, all right, so I'm going down a path, and the path is shaped like that, or the path is shaped like that. That's like short range interaction. Like each step you have to take. So if I make the path straighter, then the distance you run, R, is going to be longer, right? R, in fact, is going to be proportional to the step length, right? Times the number of steps, R times the square root of the number of steps, but well, if it's a random walk. Anyway, R is going to be proportional to the step length, but here, this interaction is going to make this end dependence like 1 over df. It'll make that thing change. This kind of long range interaction. So you're wandering around drunken, and finally you're going to cross your own path at some point. And if you say, well, there's an interaction enthalpy that makes me not do that, so I have to go that way or that way. I can't go that way. That's a long range interaction. The other one is like just neighboring, like I took this step, I can't take that step. I can't go back. Right? Or this business of like the chain rotational energies, like how that extends it. Right. So anyway, this whole thing, so if you do that, let's see. So if you do that, let's see, this should go white at some point. Not here. But the same thing. So this is another one of those random walk things. What does it say? Clicking yes will enable. Wait, I have to wait. I have to say allow editing. Maybe. Where am I missing? What's going on here? Oh wait, there it is. PowerPoint. Enable editing. That's good. Then I can. This is another one of those random walk things. So he does two, like a single chain. This is in it's in the UK. Oh, sorry, yeah. This is it's in the slides, like this thing I added in. So, oops. Anyway, it's another random walk. Oops, that's not what I wanted. Well, I can go here. Today was kind of a functional day at the beginning, and then like it's become less and less functional. So like 20 steps. So this just does a random walk, like you can watch it, and it calculates how many. It's adding a segment each time of the same, and it's doing a. So in this program, instead of saying like it's in Cartesian, it goes X, Y, Z. So he just picks an angle. If it's 3D, you just pick 2 angles. You have a step length of 1, and you have an angle, kind of angle that way and an angle out. You know, so that would allow you to do all space with just 2 numbers, 2 random numbers that go from 0 to 360. Right. So basically, that's why this isn't on a grid. It's just you end up with the same walk, whether you do it on a grid or not on a grid. Anyway, so it just goes along, and it measures this end-to-end distance, and then it's got the measures the end-to-end distance, and then says what it's expected to be. So it's calculating the expected using that NL squared thing. So that the square root of NL squared, so square root of N times L would give this expected. And if you let it run long enough, it'll get to the expected one. So, but you can wait a long time on that thing, so you can go back and do it with multiple chains. So here you can do any length you want, and then any n you want. So you can do like 100. So if this n is 100, then it should be a size of 10, like square root of 100 is 10. If it's just nl squared, n L times square root of n would give you 10. So expected thing would be 10, and you can do like a lot of runs, a lot of chains if you want. It just piles them on top of each other so you can't see it. But anyway, so here he's got his expected measured size of the thing, and then the predicted is 10. So it comes out to the right number. Like this, in other words, it works. Like the random number thing works if you do some program. And then this thing shows a plot of the number versus the root mean squared length. So the r square root of r squared average. So r squared would go with an L squared. So square root of that's called the root mean squared RMS. So you'll see that kind of all over the place, right? RMS value. So right, so the one thing to notice is that like there's a peak in this RMS value that isn't where the mean is, because the RMS is squared, so it's got like a long tail to it. So anyway, the peak of the value, the maximum value isn't the same as the mean value, but they both grow, they're proportional to each other by a constant. Okay, so the reason I mentioned that is when you want to do the self-avoiding walk, the long range interaction, you can't get this RMS value because it isn't an integer power of the thing. So I'll show you that that won't work. You can't solve it. You can't solve for this RMS value. So the only thing you can get is this maximum, which you can get if you can get the frequency and take the derivative, then find where it's 0 and just find that point. So that point is just as useful as the RMS value. It's just the RMS value is kind of what's used for Brownian motion. So it's like what we talk about. Like if you want to know the race gyration of the chain, you kind of use that number. Anyway, so this is 10. So if I make the step length 2, and then clear it, reset, and then do it again, then it should come out to like 20 here. So it's just proportional to L. If I make L 10, it'll be 100. If I make it 5, it'll be 50. Right? So anyway, so that works. Like the size of the chain, this root mean square size of the chain goes with its step length. It's proportional to it. So all these local interactions are just going to be a multiplier to make the thing longer or shorter than what it was, right? And then the dependence on n, we can get pretty quickly. So to get that, you just say the dependence on n, we just say that this is going to be, so that r squared, so you have your steps, each one's a vector, ri, rj, whatever. So there's 2 indices to it. So you're going to have the dot product of ri dot rj, they're vectors, and then find the average value of that for the whole chain as it walks through space. So that you can decompose into ri dot ri, because if the angle, so our dot product is cosine of the angle, so that thing is just going to give you 1, right? Cosine goes like 1. When it's 0, it's 1. So ri dot ri is 1, and then there's going to be like this is going to be a sum over 1 to n, so the number of molecular weights. So that's going to be 1 times n, or the step length L times n squared somehow. Oh, it's a double sum. That's why it goes 1 to n for I and j. So you end up with n squared L for that thing. And then plus the other one is ri and rj not equal to I, double sum. And that would be, so you're saying like, I'm going to step here, but it's going to be random. I can go any direction, including backwards, right? For a random walk. So like a diffusive walk. So that means that the average of that thing, the average cosine, so the average of that thing is going to give you 0, because it can just as easily go forward as backwards. So they cancel out, or you can go up or down and cancel out. So this thing is 0, and you just have that term left, and that's NL squared. So that directly gives you this thing. So that's like a definition of that. That's the definition of that R squared. If it's a drunken walk, it has to be NL squared. Random walks law. Right? So anyway, So that's kind of the one part of this whole picture of what's going on with this. Anyway, you can see there's some average size to it, but some of these are almost straight lines and some are like completely collapsed down to a spot. So you can have anything from a totally stretched out chain to like a total collapsed onto a spot chain from this kind of process, this random walk process. And also one given chain, so they aren't frozen in time, they're all moving around by KT randomly, like diffusing around, right? So this is actually how a chain would look in time also. It would go from collapsed down to fully stretched out to all these other conformations. So it's constantly like moving around. So this is like a entropically driven energy of the thing. Like it's in terms of the ordering of it, it's not ordered. It can be totally ordered or not ordered. So the entropies, there's an entropy involved in this kind of motion of the thing. So it's an entropic kind of thing. It has no interactions. Like there's no, in other words, if it had interactions, it would repel itself and it wouldn't do this. It would make a much wider kind of structure. So anyway, that's kind of the picture of this thing. Let's see. So I got the right thing. All right, so that's what this is just saying, like the two sums, and then so that's kind of that thing. So this thing, this looks a lot like diffusion. So if you take, oh yeah, sorry. All right. All right, so this equation is directly analogous to diffusion. So you talk about the root mean squared. Diffusion is going to be related to the square root of time. So that's like diffusion. So if you do a there's two kinds of limiting walks. One is a ballistic walk where you walk in a straight line. So the way you're walking is fixed and time is also fixed. So the distance you go is proportional to the time. That'd be a ballistic. So the root mean squared for that would be proportional to time. In other words, distance is proportional to time. That's a ballistic motion, meaning like a bullet goes in a straight line. And this isn't ballistic motion. This is randomly wandering around. Because randomly wandering around, the average of that will lead you to the same place where you are, like you'd go zero distance. So you have to talk about kind of the breadth of the walk that you took. So you have to square it in order to get a value from it. So the first value, you have to look at even ordered moments. So odd ordered moments go to zero, even ordered moments have a value. So the squared second moment, fourth moment, sixth moment have values. And the easiest one to work with is the second moment, which is also the standard deviation of the thing. So basically the second moment of it, the square root of the second moment is the standard deviation. So basically that's going to follow exactly the same thing. It's going to be that the only ones that matter are the ones where I equals I, then you end up with the square root time, talking about diffusive motion. That the distance you travel is proportional to the square root of time. The constant is a diffusion coefficient. So this is called a diffusive. You talk about this Brownian walk, diffusive walk, random walk, drunken walk. So there's a lot of different names for this thing. A lot of them connect back to this equation. So I mean, it's all the math of Brownian motion. You can port and just talk about this walk in the same context. So it's kind of worth, for two reasons, it's worth looking briefly at diffusion, right? So one is that this thing is a diffusive equation. The other thing is that when we talk about transport of polymers, you use the diffusive equations to talk about it because they also move. The whole polymer chain itself is going to move around randomly also in space. So the chain itself is a random walk and the chain cluster takes a random walk when it moves around in space. So you need to think about diffusion in two different ways using the same math, right? So the math is the same for the two. Anyway, so anyway, yeah, so I want to, let's see what else is in here. Primary structure, blah, blah, blah. Yeah, so there's a bunch of different names for this, like persistent chain, Kuhn chain. So Kuhn chain means that if you take a, like way we drew it, or way I drew it is like a step, right? So you have a step length called the Kuhn length. And then, so this equation is going to be like, this is the Kuhn length. Kuhn was a Swiss guy from the 1920s or something, I think. So anyway, he kind of coined this. He's a rheologist. This is a tool that's kind of used in rheology. So step is this kind of imaginary step in a sense, like a straight line step. And then this is how many of those steps there are. So you have, at this point, you have two ways to talk about the chain. Chemists made a monomer. So polyethylene's CH2, is like a monomer because it started with ethylene and then it turned into polyethylenes. You broke it open. So you have like so many ethylene units in the chain. So you have N number of ethylene units. And then you have the length of the chain R, and then you have the length of an ethylene unit, like 2.5 angstrom, 2.54. All right, so anyway, that's one way to look at the chain. Then you have Kuhn's way of looking at the chain. You have these straight line segments, and then you have so many of those straight line segments, gives you the same size of the chain. So there's got to be a factor between, but you get the same size. So you're going to have like, so you're going to have this Kuhn model where you have, so polyethylene, it's going to be like starting with ethylene, so that's a monomer. So you're going to have this chain like that, right? So you're going to have hydrogens off it. So then you could say like there's N ethylenes, and there's the length of an ethylene is 1.54 angstrom squared gives me like R squared. But that isn't right. That isn't the actual size of the chain. You need another number called C, Cn. So C would be like, just say Cn, right? So some number that converts the chemist number to the actual chain length. It's called the characteristic ratio. And then the actual length of it is this Kuhn length, which we don't know. And then the number of Kuhn lengths is R squared. And that would be the step model. It's going to take a step. So it turns out 7.6 is how many ethylene units are in an actual step, due to the fact that it can't this rotational conformational issue and whatever else happens, locally. Yeah.
Does the characteristic ratio, is that an empirical correction or is it?
No, it's a number. Like the chemist knows what he made, right? And then you have the stuff. So those are two real numbers. You know what R is. You can measure it with light scattering. You can measure it with a bunch of different ways. Or you can measure it with rheology, right? So you know what R is. You know this, the N that the chemist put in, and you know that number. And you can measure also the Kuhn length if you want, either rheologically or with scattering. And then because you know R, you can get this N, like you can know how many Kuhn lengths are in the thing. So these are all real numbers. So C infinity is a real number. In fact, C infinity is going to just be, all right, because you can say R is N, R squared is N L squared, right? But you know that the total length of the chain, L, is a fixed number. It's N chemist number, L chemist number, or it also has to equal N Kuhn number, L Kuhn, right? Because you can take this chain conceptually and fully straighten it out, and it has a length, right? So it has a physical length. That means there is this length of the chain. That means this thing is really L times L K, and that also has to equal L times L L chemical times C times this coefficient that translates it, the C that gives you R, right? So that means the C has to be like LK over the chemist number, and that's 7.6 for polyethylene. Right, so you can measure it. No, it's not like an empirical number. So it's an actual number. So you can look in the Polymer Handbook or maybe the NIST webpage, and we'll give you C infinity for. So the thing about this C is that because the chains, let's see, Mike going over, I guess second. So the chains have wiggly things at the end, right? So those things have less persistence than the middle part. The middle part is going to be more rigid than the edges. You can plot out. There. So you can plot out this C number versus position of a chain, say from a computer simulation. Right. So someplace here. So you can plot it from, say you do a computer simulation of a chain and you make it of different lengths. So you have the interaction between the units different, right? So you can change the interaction between the units. Well, as the chains get longer, so the endpoint has a lower C infinity than the middle part. C. So it's going to be C to the N, and then it'll go to C infinity when you get an infinite chain with no N lengths on it, N units on it. And then it's just like what the middle is on average. Because the ends are always going to be floppier than the middle. Right, so that means they're going to be more wiggly, whatever. They're going to have a lower persistence length. So C infinity would be like, as you like, or you could do a plot and a computer simulation can measure this persistence throughout the chain, right? So you can actually measure it for different units and plot it. Then you can take the middle number or the plateau number. At some point, the chain gets so short that you never reach a plateau. Like that's an oligomer kind of thing. Like you can't actually see any real persistence to it. It becomes just a continuous function. Right, so there's some ambiguity about this number in that you can't buy an infinite molecular weight chain, or you might have polydisperse or whatever, right? So basically there is ambiguity a little bit from a fundamental perspective. There's an actual number, C infinity. So, and you can look at different molecular weights and extrapolate to C infinity if you wanted, right? So, right, so there is a way to measure. It's not empirical. I think it's the deal. So yeah, I think I'm out of time now. So I'll pick up here. I guess next time I'm going to talk about this Brownian motion, like one little bit about Brownian motion. So
I thought I might get one here. I doubt he looked at it, so I was like, oh. Yeah. One of the people in my group, I thought her response and like a meeting for tonight for like just one girl who we have been communicating with. But it's not a meeting for tonight for us to like compare everything, and she hasn't like accepted the time or like anything.
yeah,
So
I'll just put her in a group on her own,
yeah.
It's like late for this week, maybe for like next week, So just live with it this week and
Okay.
I don't know.
I don't know.
Like everyone's gonna do okay, but it isn't
Yeah.
really fair. Like it makes you feel unmotivated when that happens, so
It's just like, I feel one, like, I don't know, if, like, maybe she's trying to like get towards me and she can't, if I someone's like not gonna.
could be she's sick or something,
Yeah.
broke the leg or whatever.
I'm more concerned, but
Like weird stuff has happened a
Yeah.
lot of times, so it isn't like,
Yeah.
it's not possible, but basically the way I've been doing it, I taught that Africa class last semester. I just put everyone that didn't show up into one group, and actually they did a lot of work then.
yeah.
It's just kind of weird because then they were like, oh, I have to prove that I'm
Yeah.
doing something,
Okay.
So, but grade wise, it won't impact,
It's- Yeah.
I mean, don't worry about it.
It is the graduate student that we can, but hopefully
Okay.
me and the other girl can like.
All right.
Figure it out.
I'll just move them next week, I think. I think it's okay with you. I mean, like, as long as you get above an 80,
Yeah. I'm
that's an A,
not Too pressed.
and
about-
it's only whole grade, so it doesn't matter. So basically don't worry too much about the grade, but it's kind of like demotivating. I think
Yeah.
it's the main thing,
Yeah. I
so-
think me and her will figure it out.
I'll just park them in their own group and then they can,
Okay. I can send you an email and like let you know if they do end up responding tonight, because maybe they did see the invite and are gonna join.
yeah. The grad students